Okay, with the test in torque coming soon, it's time for us to move to the next unit, which has to do with momentum. It's actually going to be momentum and energy, but we're going to start with with two-dimensional momentum. Now, we did momentum in grade 11 physics, so before we get to two-dimensional momentum, we should probably review momentum and impulse. If you remember, momentum is a small p, and an object's momentum is dependent on both its mass and its velocity. So you can find an object's momentum by just doing p equals mv. What's momentum measured in? Mass is measured in kilograms. Velocity is measured in meters per second. That some of you might remember last year we called a Kelly. It's not really, in physics, we're not as concerned about an object's momentum as we are its change in momentum, right? A car needs to change momentum to come to a stop. An airplane needs to change momentum to take off or to come to a stop. A train, the same thing. You'll often hear people say their momentum was too big, they couldn't stop. And that's true for things like trains. When they see something on the tracks, they put their brakes on as much as they can, but their mass is so huge that they can't often bring their momentum to zero. So change in momentum is delta p. Now, to get delta p, you could try to change the mass, right? You're driving down the road, the light turns red, you need to bring your momentum to zero. You could press the eject buttons on the passenger seats of your cars and get rid of the mass, but usually instead it's our velocity that changes. So it's delta p is equal to m delta v, which really is saying delta p is equal to m brackets vf minus vi. All right, now, so what do you have to do if you want to change an object's momentum? Well, to change an object's momentum, you have to actually apply a force, right? So you're going to apply a force on an object. So you're driving down the street and the light turns red. You need to step on the brakes and apply a backward force in your car to bring your velocity to zero. You have a couple of choices. You could see the light turn red when you're a few hundred meters back, and so you could gently step on your brakes and apply a small force over a fairly long period of time. Your other option would be like, I'm pretty far back, I'm not going to step on my brakes yet. Yeah, I'm still far back, not yet, not yet. And then you're like 2 meters from the red light, and you put all the force you possibly can on your brakes for a really tiny period of time to try to attempt to get your momentum to change enough to bring the object to zero. So when we want to change an object's momentum, we have to apply a force over a period of time. And the result of that is the change in the object's momentum. Okay, now this side then is the change in momentum, delta p, and this side is known as the impulse, J. Okay, so last year we talked about the impulse. And the impulse is a force applied to an object over a period of time, which causes a change in the object's momentum. Now, if you look at this, you realize, okay, if J is equal to F delta T, and F delta T is equal to, really, that's M delta V, and if M delta V is equal to delta P, then J must be equal to delta P. And J must be equal to M delta V, and delta P must be equal to F delta P. So for those of you that had me last year, we had this box with 4 corners where any pair of corners was equal to each other. The one other interesting little thing is, I'm just going to rewrite this. F delta T is equal to M VF minus VI over VF minus VI. If we were to divide both sides by delta T, then you'll have F is equal to M, and in brackets, VF minus VI over delta T. VF minus VI over delta T from grade 10 is our grade 10 equation. It's just ma. And so the impulse change in momentum equation really comes directly from Newton's second law, F equals ma. Okay, so last year we did a number of questions with these, and then we moved to something that was called the conservation of momentum. And actually, it was really called the law of the conservation of momentum. It's a law. The fact that it's a law means it always is true. And it's like any of the other conservation laws that you may have heard of in chemistry or in physics. Conservation means the total doesn't change. So whatever the total momentum was before an event or an occurrence, that's what the total has to be after. So the law of conservation of momentum says the total momentum of a system before an event has to equal the total momentum of the system after the event. Okay, the total momentum of a system before the event an event has to equal the total momentum of the system after the event. What do I mean by event? Well, an event could be several things. It could be a ball rolling and smucking into another ball, right? The system would be the two balls. The event would be number one running into number two. If number one had a certain velocity initially, maybe let's say of 5 meters per second going east, and it smucked into number two, which was perhaps initially at rest, if we knew the masses of these two balls, we could find what's the total momentum before the collision. And then we could figure out how fast we're each going after, and the before and the after need to equal. Okay, so P initial total must equal P final total. In other words, M1V1 initial plus M2V2 initial plus however many other particles we have in the event initially, we add up all of their momenta, and the total has to equal M1V1 final plus M2V2 final plus ... for however many other components of the system that we have. Okay? So now in grade 11, all of our collisions were linear. So all of our collisions were ball 1 runs into ball 2. Okay, so this was V1 initial, and we up there said 5 meters per second east, so we may as well keep it. V2 initial 0. And then after the collision, ball 2 goes off in a straight line. So let's say V2 final is maybe 2 meters per second east. All right, and then the question might be, what's V1 final going to be? And we'll pick some masses here. Let's say M1 is 3 kilograms, and let's say M2 is 5 kilograms. Okay, and so then the question would be, what's V1F? So give it a try to see if you can remember how to do these. Last year, most of you found them fairly straightforward. So pause me for a second and try it, and then come back. All right, assuming you pause, so it's M1V1 initial plus M2V2 initial is going to equal M1V1 final plus M2V2 final. V2 initial is 0 because it wasn't moving, and you're looking for V1F, so bring this one over. So it'll be V1F is equal to M1V1 initial minus M2V2 final, and then divide by the M1. V1F equals, what did we say they were? 3 kilograms times 5 meters per second minus 5 kilograms times 2 meters per second divided by 3 kilograms. 15 minus 10 on